Okay, so now that we have the notation and the terminology down, let's define our first kind of formal probability model. And we're going to define one in terms of equally likely outcomes. All right. So to start, we're going to suppose omega is finite. And that every omega is equally likely. Meaning that it occurs with the same frequency. Then what we can do is we can define a probability distribution on omega that we call the discrete uniform distribution. Now, why do I put discrete in parentheses here? Because it's a little bit redundant. We don't actually have to say discrete explicitly because it's implied. And we'll know we'll throughout the course, it's not really relevant right now because we haven't gotten into it yet, but there is a distinction between terminology called things that are called discrete, things that are called continuous. And we will sometimes need to distinguish between those things. Right now, we've only talked about discrete things, so it's a little bit unnecessary. It's also obvious um, from context that what we're talking about here is discrete. But don't get distracted by that terminology. It's a uniform distribution. What uniform means in probability is that everything has the same value, or in this case, everything's assigned the same probability. Okay. So formally, how do we formalize this? We're going to define a function P is going to be defined from the power set. Remember, we define the power set up here. It's the set of all subsets. It's a function into the unit interval, so it's going to assign some value between 0 and 1. The way that we're going to define it is that to every set, so P is the function, A is the argument, A is a subset of omega, we assign the value by definition as the ratio of the size of A to the size of omega, where A is a subset of omega. Okay. That is the definition of the discrete uniform distribution. This is a probability distribution. How do we interpret this? So interpretation, by the way, interpretation, extremely important. It's one thing to understand. It's one thing to be able to do the math and manipulate the symbols. It's quite another thing entirely to be able to actually understand what we're talking about at an intuitive level. In order to be able to use any of this stuff in real life, we have to know what it means, know how to interpret it. How do we interpret this? Think about it as repeatedly running some process, and let's suppose that process is described by P. So we repeatedly draw from P and define, let's define after we've drawn n times, right, we're going to define something called f sub n. When I write colon equal sign, I mean, I'm defining a value as that, right? That's different than when I say 2 plus 2 equals 4. I'm not defining 2 plus 2 to equal 4. That actually just is what 2 plus 2 is equal to. Here, I'm setting f sub n. I'm defining a symbol, and I'm setting it equal to 1 divided by n times the number of times that A occurs in the first n trials. Okay, so it's the ratio. How often, as a proportion of n, as the proportion of times I've drawn from I've done this thing, I've run this process, how often has A occurred? Well, the interpretation, this is the frequentist interpretation, but it is the interpretation, is that as we do more and more draws, f of n will converge, will become closer and closer to P sub A as n goes to infinity. Okay, so that is it's the long-term frequency. It's how often we expect this thing to happen as we draw more and more from the distribution. We repeat the process. Okay. Let's do the dice example. Revisited because we are going to put it in the terminology that we're now setting, the formalized terminology. So remember, what was the sample space omega in the dice example? We have two six-sided dice. Okay. Omega was pairs I and J, such that I equals anything from 1 to 6, and J is equal to anything from 1 to 6. Okay. So what does that mean in this context of the uniform distribution on these outcomes is that we define P of A as the size of A divided by the size of omega, which is 36, for every possible subset of omega. I don't know why I use square brackets up here. It doesn't matter. Use parentheses, square brackets, doesn't matter. I don't want to confuse anybody by that, but I know that when you're new to a topic and you see any slight change in notation, you start to it can be confusing. And so my apologies for that. Let me just be consistent with this to start, but fair warning is that I might not be able to maintain that consistency throughout everything, all of those courses. But okay. So now that's the bare bones sample space definition of the core probability model. But what we're interested in a lot of times, like in the game craps, what are we interested in? We don't care about this. Well, sometimes you do if you're betting hard ways or things like that. You do care about the exact combination of the two dice. But really what you care most about in most cases is the sum on the two. So let's define T sub j to be the event that the pair of ij such that, geez. No. Hey. Okay, let me not use. All right, let's do this. Define it as T sub K as the pair I and J such that I plus J equals K. And this is going to be for all possible K from 2 up to 12, right? The only possible sums of two six-sided dice is you go from 1, 1, which is 1 plus 1 is 2, up to 6, 6, which is 12. Okay. Let's calculate these. So each one of these T sub K's is an event, right? It's a subset of omega, so it's an event. So let's calculate their probabilities. Let's put it in a table, okay? All right. So let's put a table here. Probability. So for each K, we're going to express the probability of T sub K under the uniform probability model. So it's important to understand that all of these probabilities are under an assumed model. The assumed model that we have is this. This is our model. Cannot stress that enough, and I'll talk about that in a minute. I'll do a little tangent in a minute. I don't want to get off on a tangent right now, but let's take all possible values: 2, 3, 4, 5, 6, 7, 8, 9. Hope these fit, and they will. Okay, nice. 12. Very good. What's the probability of the sum being 2? You're going to want to work all these out yourself, but the way it works is, well, let's just do it. Let's just do it. So I'm tempted to just write down the answers, but that would be lazy of me. And that's maybe a little bit of a lesson in there. The shortcut is not usually the way to go until you have enough. You really have to have enough knowledge and enough intuition built up and mastery of the subject to justify taking shortcuts. So my advice would be, especially when starting out on this topic or any topic, especially in math, but is don't take shortcuts. Don't try to do it fast. There's no reward for that. So over here, we're going to have I, and I can be 1, 2, 3, 4, 5, 4, 6. J can be 1, 2, 3, 4, 5, 4, 6. And we're going to put the sum in this table. Why I have to make it a matrix. Let's do this. It's very tedious, but that's just the way it is. So let's put the sum. 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4, etc. So trust everybody here can do this. I'm going to fill it out. 2 plus 2 is 4. 2 plus 3 is 5, etc. Oof. Exhausting, but if you want to do it right, you have to do it right. You know what I mean? All right. Oh, hand's starting to hurt. Okay. Here we are. So now we're trying to calculate probability that the sum is 2. T sub K is the sum is 2. How many are there? How many ways? In order to do that, we have to count the number of elements in T sub 2. How many ways are there to add up to 2? There's just this one here. Okay, so that's just 1. And we divide by 36. So the probability is 1 divided by 36. How about 3? Well, 3 is here and here. There's 2. 2 divided by 36, therefore, is the probability. How about 4? 4 is interesting pattern here. It's just these kind of anti-diagonals of the matrix are starting to appear. So there's 3 4s. Many 5s, boom, 4 of them. I'm obviously going to run out of colors in a minute. Maybe I will, maybe I won't, but there's 5 6s. Actually, they have more colors here. Let's do purple. 7. 6 over 36. All right, let's go to 8. 5. That's pretty nice, actually. Let's see. Gray. 9. There's 4. Not gonna let me. Oh, there you go. Let's see. Tough one. Think they'll let me. Well, all right. Do brown. It's 3 10s. Do dark green for 11. Yo 11. And finally, dark blue. 12. All right. There's 1 12. Okay. So there you have it. I'm going to color code this whole thing because I think that that's kind of nice thing to do. 7 8 9. What was 9? 9 was gray. 10 was brown. 11 was dark green. 12 was dark blue. So fully color coded. Okay. So that's your distribution. That's the distribution was defined. The probability model is defined on outcomes. It's uniform on all the outcomes. That doesn't mean that all of the possible events are uniform, right? Because the events are an accrual or an aggregation of outcomes. There are more ways to make a 7 than there are to make a 2. Okay. So let's calculate some events. So let's consider the event of a 7 or an 11 as the sum. Well, of course, we can do this ourselves. If we really want to go explicit, we would say, okay, how many ways are there to make a 7? 1 plus 6, 2 plus 4. Let me stop writing these parentheses because it's taking too much space. 1 6, 2 4, 2 4. What are you talking about? 2 5, 3 4, 4 3, 5 2, 6 1. That's the 7. How about the yo? The 11, 5 6, 6 5. That's 8 total possibilities. This event can also be written as T sub 7 union T11, right? So in our set theory, this is the union of 2 events that we've already calculated the probability of. So what's interesting about this probability of this event E is the probability of the union of T7 union T11. Okay. We've already calculated this as 8 over 36, right? Because the size of E is 8. We've counted at 8. But what is 8 over 36? 8 over 36 is equal to 6 over 36 plus 2 over 36, which just so happens to equal probability of T7, which you've calculated above, 6 over 36, plus the probability of T11, which we've calculated above as 2 over 36. Okay. So we'll come back to that. That's not a coincidence. But we do have to be careful. Let's now consider the event E. Well, yep, the event E, which is not a 2. Anything but a 2. Okay. Well, not a 2 is T2 complement. And T2 complement is to say, well, if a 2 didn't happen, then a 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12 must have happened. So that's a T3 union T4 union, etc., up to T5, T12. How many ways are this to happen? Well, we know that T2 has one event, one outcome, because we counted it. So what does T2 complement? Well, T3 has 2, T4 has 4, T3 has 2, T4 has 3, etc. Well, we just count everything in this square that's not a 2, and it's going to be 35, right? So by definition of this model, probability of T2 complement is 35 divided by 36, which incidentally is 1 minus 1 over 36, which incidentally is 1 minus the probability of T2. These are examples of general principles that we're going to find over the next, as we continue to generalize this. Finally, notice that the probability of omega, what is the probability of omega? It's omega is the event here, because a set is a subset of itself. So it's the number of omega divided by the number of omega, 36 over 36, which is 1. Okay. Note also a couple other things. For every omega, 2 to the omega satisfies. So the set of all subsets satisfies a few general rules. It contains omega. So omega is a subset of itself. If if A is in omega and B is in omega, then the intersection is in omega. And therefore is an element of 2 omega of the power set. And if A is a subset of omega, then the complement is a subset of omega, which again means that A complement is in the power set. let me make this consistent. Omega is a subset of itself, which says that omega is an element of the power set. Okay, something to highlight here. There's a difference between the subset symbol and the element symbol. Okay, what is it? When I write, this is a relation between sets. Right, so A intersect A subset of B is a relation between sets. In other words, what? A is a set, B is a set. We're regarding A as a set, we're regarding B as a set, and we're saying A is a subset of B. When we write something like A element of 2 omega is actually a relation between an element and the set. So in this expression, even though A in and of itself is a set, we're actually treating it as an element. We're regarding it as an element, and we're regarding it as an element with respect to the set, the power set. We're saying the power set has sets as its element, and this set A is an element of that set. Okay, a little confusing if you're not familiar with it, and so something worth thinking about. Last thing I want to say, and I'm going to wrap up this section, and then we're going to move on and talk more about we're going to actually go into the precise axioms of probability next. I want to make clear that, so here's a model that we talked about for dice, okay? And the model is based on the uniform probability model, the uniform model on all possible outcomes. This is, by the way, the model that's underlying, you know, most games involving dice, particularly the game of craps, for those who are familiar with the game of craps. This is the model that's assumed in, when a casino offers odds, right? If you go into a casino, you play craps, there's various odds associated with playing craps, okay? Those odds are based on this probability model. I'm not going to go into it more than that right now because we haven't talked about important concepts that are necessary, like expected value, things like that. We will. Okay. It's important to understand that it's not a God-given thing that the game of craps obeys this model. When you roll 2 dice, that it automatically obeys this equally likely outcomes model. It's the other way around. The dice behave the way the dice behave. We're trying to model the real world, right? The real world doesn't necessarily behave the way that we think it does or that we want it to. Certainly, you can find dice that are loaded or weighted in an unequal fashion so that the results will actually come out different with different frequency. Remember, how do we interpret this is we can validate this model by saying, let's roll these dice 1,000,000 times. Let's count how many times each of these outcomes occurs. And what should happen after 1,000,000 draws is that these frequencies should match up with the theoretical probabilities if our model is correct. That's pretty much the whole premise of statistics is we collect data. We have a situation we're interested in. We fit a model, or we describe a model to say, this is how we think this thing is behaving. We collect data to validate, is the thing behaving that way or is the thing not behaving that way? That's one of the things we do in statistics. Another thing we might do is we say, I don't know exactly how this real world situation is behaving, but my assumptions are going to be that it follows these basic properties. And here's a bunch of different possible models that have those properties. We then collect data and we say, okay, given the data and given the possible models that have the properties we want, which model is the best at describing the data? How do we make the most sense of the data given what we've observed? That's what statistics is all about. Probability is the foundation for it. So I just wanted to make that comment, is that if I say I'm rolling 2 dice, what's the probability of 7? Your answer would be, I don't know, because I haven't given you a model, and you would have to make assumptions. You know, what assumptions are we making about the dice? In this example, the assumptions we're making is that all outcomes are equally likely. Once we have that assumption, we can specify this particular model, and these probabilities come from that model. We could specify a totally different model, and in that case, the probabilities would be different. But I would have to say that this is my different assumption about how the dice are behaving. Okay, so I'm going to stop there. We'll have plenty of opportunity to clarify those things throughout the course. And let's come back and generalize this and actually come and describe what the probability axioms are.